Hello everyone, my name's Dan Handley and I'm a firmware architect at Arm. And in this session, Sophie, Matthew and I are going to talk about firmware for the Arm confidential compute architecture. First of all, we're going to have a recap of the Arm CCA tech event in June, as there are a lot of concepts, ideas and terminology from that day that we're going to use here. After that, Sophie's going to talk about the TFA upstream status, including the four-world support for the Arm CCA. And he's going to talk about some of the ongoing investigations in TFA, for example, around measured boot, Granule Protection Table library, and the saving and restoring of vector register context on a world switch. The Arm CCA tech event on the 23rd of June contained a number of presentations, and I've provided a link to the slides and the videos there. It contained an introduction to the Arm CCA, including an overview of the hardware architecture, the realm management extension. Arm CCA consists of both a hardware and a software architecture, and there's a separate presentation on that software architecture discussing the goals, concepts, and key components in the architecture. There's another presentation on the attestation architecture, which is a key component of the Arm CCA for realms to establish trust in the execution environment they're in. There was a presentation on the developer resources describing where to find the specs, tools and prototype implementations, and how to get involved in ecosystem software enablement. Finally, Sophie gave a deep dive on the TFA monitor firmware, describing the changes needed to support Arm CCA at EL3 and specifically the TFA prototype implementation. And this presentation is effectively an evolution of that story. So what's confidential compute? Well, most people are aware of technologies like disk encryption for protecting data at rest, or transport layer security for protecting data in transit. Confidential computing is about protecting data that's in use by performing computation in a hardware-based secure environment, shielding portions of code and data from access or modification, even from privileged software. The Arm A profile architecture already contains a number of technologies to help with confidential compute. For example, Trust Zone enables isolation of secure services from an OS or hypervisor. Virtualization technologies allow services in guest virtual machines to be isolated from other guests or the host operating system. And that virtualization technology is also available in the secure world since version 8.4 of the architecture. Arm CCA goes a step further and now allowing isolation not just from the host OS, but also from the hypervisor and even Trust Zone. So what does the Arm CCA hardware architecture or realm management extension add? Well, fundamentally there are two new security states and physical address spaces. So in addition to the non-secure and secure physical address space, there is a new realm physical address space or PAS for confidential compute. Realms VMs run in realm state but are managed from the non-secure state. There is also a new root physical address space for EL3 firmware. Prior to Arm CCA, EL3 firmware is not physically isolated from other secure exception levels. There is a new Granule Protection Table which determines the current PAS of a page, and that's dynamically managed by a monitor, allowing pages to move between PASs at runtime. There's a Granule Protection Check hardware attached to the MMUs and the CPUs in the system, which checks the GPT on access and faults any invalid accesses. This provides the access table on the bottom left, where the root PAS can access everything and is the only thing allowed to access its own PAS. Non-secure can only access its own PAS, and secure and realm software is mutually distrusting. Finally, root, realm, and secure memory is encrypted with a key per PAS, and those keys are renewed on each boot. The Arm CCA consists of this realm RME hardware, but also CCA firmware. That CCA firmware includes a new component called the Realm Management Monitor, and Arm will be defining a specification to standardize the interfaces and execution environment for an RNMM. That includes a realm management interface for the hypervisor or OS to manage realms and realm memory. There will be also be a Realm services interface from Realms into the RMM to provide services like measurement and attestation. It's important to say the RMM will have no policy. They just respond to requests from system software. The Trusted Firmware project will be providing a reference implementation of the RMM firmware, and Arm will be contributing the initial version, but it will be an open governance project like other Trusted Firmware projects. CCA firmware also consists of impacts on monitor firmware and other firmware running in root state, and the reference implementation of that will be contributed to TFA, and that will be the subject of the later slides. Finally, there is also trusted subsystem firmware, that is firmware that contributes to the Arm CCA security guarantees, for example, the system control processor firmware or hardware enforced security, which I'll talk about in a moment. So the Arm CCA strongly recommends the use of hardware enforced security. Hardware enforced security is an isolated hardware subsystem that allows you to store and process secrets outside of the application processor, for example, in a secure element. And this separation aids the threat model by reducing exposure of critical secrets to the application processor. HES services are only available to AP root state firmware or trusted subsystems. HES services include things like measurement storage and retrieval of those measurements in the form of signed attestation tokens. In Arm solutions, HES firmware will load the initial boot firmware of application processor and the trusted subsystems, so the initial boot will no longer be in ROM. With that, I'm going to hand over to Sobi to talk more about Trusted Firmware-A.
Hello, everyone. We will do a quick recap of the impacts on TFA due to introduction of Arm CCA as explained during the tech day. The different items listed in the slide capture some of the main aspects. It does not capture all the different changes that need to be done in TFA, but some of the main aspects are captured here. As Dan mentioned in the previous slides, the EL3 monitor firmware will execute from a new root pass. Since the root pass is isolated from secure pass, all of the different stages of EL3 firmware must be loaded and authenticated in root pass. The diagram on the right-hand side shows the envisaged boot flow in an Arm CCA system. Every block in that diagram is a firmware image that is executing during the boot phase. The yellow blocks are executing in root pass. The orange ones are in secure pass. The blue block are the non-secure binary images, and the purple one is the new RMM image running in the Realm world. So now BL2 needs to be replaced by two loader images, namely root boot firmware and secure world boot firmware. The root boot firmware runs in root pass and loads all the root world images, the RMM, and also the secure world boot firmware. The secure world boot firmware loads the rest of the secure world images, all the red blocks, the red or orange blocks in the diagram, and also the non-secure bootloader. RMM needs to be loaded into a static carve-out NDDR assigned to Realm world. So now root boot firmware will need to create this carve-out using the Granule Protection Check hardware. The EL3 monitor firmware needs to manage the CPU context of the Realm world at runtime. So the management involves saving and restoring the CPU registers as part of switching the worlds. But there is a caveat here for SIM-DSVE registers, which I will elaborate in a later slide. A new dispatcher component, RMMD, needs to be added. A new software library to create and manage Granule Protection Tables and enable GPC needs to be added. We also will add a test Realm payload, need to add a test Realm payload to test the monitor firmware. As part of the CCA Tech Day, we also upstreamed the TFA prototype branch on tf.org. So the prototype branch does not implement all of the enhancements mentioned in the previous slide. Only Realm and non-secure paths are supported in this branch. The TFA branch and TFTF branch URLs are mentioned in the slide. So the below diagram shows the test setup, how to test the prototype branch using TFTF. So TFTF has new test cases to issue some RMI calls, which will be routed via BL31, and the RMI calls will be handled by the test realm payload TRP. And depending on the call, the TRP may invoke Granule Transition Service to demonstrate migration of granules from one pass to another using the Granule Transition Service. Next, I will discuss the upstream status and for-world support. So we have pushed a patch stack enabling for-world support on tf.org. It's available for review. So in this, utilizing this patch stack, we are able to run secure and realm world software stacks, each having their own isolated software. Memory protection is enforced via GPC. TFTF runs SPM and realm world test. So within this patch stack, a new build parameter RMM is introduced to point to the realm world payload binary. This is similar to the BL32 parameter for the secure world payload. BL31 supports two dispatchers, one each for the secure and realm world, and can route SMCs to the respective world. All the changes in the patch stack are under feature RME build flag, and these changes are under our experimental features of TFA. We also plan to add more tests to TFTF to test both realm and secure world together simultaneously in future. In the next slide, we will discuss some of the ongoing work and investigations that we are doing within the team. So first, I will mention the measured boot mechanism utilizing HES. So Dan mentioned about HES in the previous slide, the hardware enforced security module. The diagram shows two schemes for implementing measured boot. For the sake of simplicity, we are assuming that BL2 loads all the firmware images. The left-hand side diagram shows the scheme envisaged for a traditional two-world system where you just have a non-secure and secure world. So all the measurements are made by BL2 are captured in a event log in secure memory, and then it needs to be relayed to a secure partition, which then deals with storing these measurements either on a physical TPM or a firmware TPM. The secure partition later at runtime interacts with the normal world entity to retrieve the measurements made. So this could be UEFI, and it could be via TCG mandated TPM commands, which will be used for platform attestation. On an Arm CCA based system with HES, BL2 records all these measurements directly to HES. It is likely that both the methodologies will need to exist at the same time in BL2. This is because the secure partition will deal with the traditional platform attestation flow, and the realm attestation will be a different mechanism, not involving the secure world, and this will be specified in the RMM specification. So the current implementation of measured boot in TFA is a proof of concept. It has got severe limitations. So it doesn't measure all the images loaded. For example, it doesn't measure the configuration files, and also it doesn't measure the secure partitions secure partition. So we are enhancing the measure boot implementation in TFA to cover all the images loaded during the boot phase. The measure boot scheme should also cover critical data in the system. So there is analysis and design undergoing in this area. EL3 monitor also needs to host a runtime service to allow dynamic attestation of realms. Next, I will discuss about some of the enhancements we're doing to the Granule Protection Library. So the Granule Protection Library needs to support the way in which DDR will be initialized and discovered, and how the GPT, the Granule Protection Table management, will be split between the loader phase BL2 and the runtime phase BL31. The Granule Protection Table has two levels of tables. The level 0 table entries can be either block entries or it can point to L1 entries. A possible GPT initialization sequence is shown on the right-hand side top corner. So BL2 initializes the L0 tables as block entries with GPI any or access any attribute in SRAM for the entire address space of interest, and GPC is enabled. Then BL2 progresses to discover the extent of DDR, and after the DDR is initialized. The L1 tables are created for this discovered DDR range with root, realm, and secure world carve-outs. And for creating the carve-outs, we will mark them in the L1 tables. And the L1 tables also need to be created in root pass. The Granule transition service in BL31 later on will transition memory from one pass to another at runtime by manipulating the Granule protection tables. So the library in Upstream needs to be enhanced to support the above sequence. We are also doing some investigation on how to use the contiguous descriptor for reducing TLB invalidation pressure during pass migration. Both RMM and SPM will make use of the Granule transition service for the use case. In case of SPM, it will use Granule transition service for fulfilling dynamic trust zone use cases. Previously, I mentioned that during world switch, EL3 monitor firmware must manage the CPU register context. For SVE and SIMD register context, the current direction is that EL3 monitor should not manage them, but it should be the highest privileged software entity of the respective world that should be responsible for this. The main reason for this is that it allows the efficient implementation of lazy save mechanism of these registers, which is very essential for performance, as these register context sizes are big, around 8 kilobytes for SVE. It would be very difficult for the EL3 monitor firmware to implement lazy save mechanism in an efficient manner. As you can see, as part of save and restore, we need to save the incoming SVE context and then restore the VM specific SVE context, and EL3 has no knowledge about the VMs or the secure partitions running. This also, keeping this mechanism out of EL3 helps in keeping the EL3 monitor firmware memory footprint small and also reducing some complexity. There is a case where EL3 must be involved. This is when the realm world is preempted by a secure world interrupt. Since the realm world SVE context must not be leaked to secure world, in this case, the EL3 monitor must temporarily stash the SVE context of the realm world. It must clear the SVE registers and then hand over control to the secure world for handling the interrupt. And once the interrupt handling is completed, it will then return control back to RMM and also restore the SVE context. There are some optimizations that can be done to make this transition more performant. We could indicate to the SPM that the interruption was from the realm world, so it does not need to save the incoming SVE context. This is an area of investigation at the moment. That's all I had to mention regarding the enhancements done to TFA, being done in TFA for Arm CCA. Thank you everyone for attending the session. Please feel free to ask any questions that you may have. Thank you.